Morning.
Good morning.
Morning. So I wrote to you yesterday.
Yeah.
Yeah, so if you would provide me a couple of details about the capstone project. So what are the requirements, how much time it should take? Because I don't know what is a capstone project. We used to have theses in here. So I never supervised a capstone project. What's the difference between capstone project and the thesis? I don't have this model in my mind. So if you could tell me a couple of things or write in Slack a couple of things about the capstone project, that would be useful.
To be honest, I think it's not really difference. I think it's the same.
Hey, Simon.
Hi, Simeon. Okay, but I just I don't see a message.
It's in this my channel that you have created yesterday.
I think I thought that I deleted, but it seems like because I then wanted to switch to
your personal
messages. Personal, yeah. Sorry.
No, it's okay. It's okay. No problem.
So maybe if you resend me to this personal.
Sure. Yeah.
Okay.
But otherwise, of course, it's just it is important to understand the scope so that I would understand what's your.
Yes. I agree that if it's feasible or not, to do this in some reasonable time.
Yeah. So how much time you have? What is expected? What is it that you yourself expect? What is it you yourself want in that sense? So yeah, all that kind of things. Once that, I mean, we could actually have a separate call and then just discuss these things together and then figure out what can be done. Because I actually have in a project, I have one person who's left because he applied for a PhD in another university. And we definitely would be willing to give out this as a project. And this is based right now on the publicly available data. So data is up there in internet and we can just grab it and do whatever analysis we want and see what comes out of this. If you could do just a proof of concept on the publicly available data, that would then be possible to replicate in our personal in the autonomous driving lab. So the car that we have here, we would be able to collect the same data and then see if the same thing works on our data.
Yeah. Okay. So yeah, maybe it makes sense that I also make some preparation and then we have a call to discuss details. So when do you have time?
That's a very difficult question, but let's just ping me. Just say, hey, let's talk about this. Then I will figure this out. So.
Okay, great. Thank you.
How are you guys today? What's the mood? Yesterday, I felt that you were guys fine. All these things were like okay.
Yeah.
Okay.
It's really rainy weather, and a little bit, let's say, sleepy. Raining, no sun. So this is difficult. But the lecture is great, but the weather.
We have a nice weather for some days. Usually it's the other way around. In Kiev, it's usually better, and then in Tartu it's cold. And we recently had a spring basically in Tartu. It came like a couple of weeks ago. Before that, we used to have just a winter in its spring version of the winter, basically. And that's how the weather in Estonia is mostly like throughout the year. But now we have white nights. Do you know what white nights are? So basically almost have no time without sun. It's almost never going down.
I heard, but never saw it. Let's say myself, didn't feel it myself. So
yeah, it's when you go outside at like 11 something, and it's like at 5, maybe 4. I don't know. So not quite whitish to my liking, but it's quite fun and natural. Simon, how are you doing?
Fine.
Fine. All good.
Yeah, thank you.
Right.
I'm also looking on the rain outside.
You both guys from Kiev?
Yeah.
Currently, I'm sitting, let's say, have lockdown, quarantine in Abuchiv. It's near Kiev, south to the Kiev. So, but you mean originally, or because originally I think we are not from Kiev. I'm from Dnipro city.
Dnipro, okay.
Yes.
I'm from Konotop city.
Konotop. Oh yeah. I'm from Kherson city, so I wouldn't call it city. To the very best of my understanding of what city is like. I mean, I wouldn't call Tartu city, to be honest, because it's too small. But it's definitely a town. Yeah, for sure. Alexander, morning. Oh, night to in your case. Oh, Igor is here. Igor is also here. And Olga is here. Hey. She's watching after you guys, making sure that you're all here and study. And Lena showed up. Great. Well, we have almost the entire crew. Only Kenneth is missing. So I think we could make another minute just to catch him up. Anybody wants to share anything? Like, you know, this kind of, we are here for you, all that kind of stuff, no?
No, just good morning to everyone. This holy Shabbat is really good to spend on study.
I'm actually, do you know if you can actually like study on Shabbat? I'm not entirely sure. I know that you cannot make fire, which used to be basically switching on the light would be included into making fire. So you should have somebody pushing the buttons for you, like switching on the light and elevator and all that kind of stuff. Don't ask me how I know it. I read Richard Feynman's book, and he was making fun of this quite some time. Olena here. Olena, how are you feeling? Just don't ask these kind of questions. All right. I'm not asking these kind of questions. It's quite late.
To be honest, I didn't get this last email that we have a lecture today at 8 or what? I think it was from Olga mail.
What the lecture?
Olga,
can you comment on this? What was
yes, it's a lecture with lecturer Patsurko, Natalka. As she couldn't make the yesterday because of her schedule, so she asked to replace it for today on Saturday. But but she highlighted that it's not like a consultation, but it will be like a lesson. So it's really, really very advisable to be there.
I do not see this lecture in my agenda.
In the calendar?
It should be there. Maybe it's if you are the student of it's for the class of advanced analysis of public opinion, and if you're taking this course, you
no, I know.
Then you are free.
The confusion that the topic of the email was machine learning and time series modeling class. This is that's why it was confusion. That topic of the email was machine learning and time series, and I couldn't recognize that it's regarding the different course.
Yeah, okay, sorry, this is the my mistake. Yeah, it's for the another course.
Okay, great.
That's not me, guys. That's not me. I'm not to blame here. All right, so I'm just thinking that, well, we should slowly start because there's a lot of things to discuss, lots of things to look at. Simon, if you could mute your mic at some point, that would be nice. Yeah, so let's get started and let's see where it gets us. Olena is sleepy because she wants to sleep. We are sleepy because we also want to sleep. So everybody is sleepy. Everybody is on the same page. Great. I love it. So let's do it. Let me share my screen. So this would be that one. Yeah. So just to kind of quickly remind you what we were through, right? So we were through a lot of things yesterday. We have, I think this is the most important. We have visualized a grid of points which we could visualize, which we could predict, and then which classes we can visualize. So we could get to see what actual classifiers think about each of the arbitrary spaces, right? So we could look at any space anywhere, and you would know exactly what would be the class of the point that would land on that space. Which is pretty cool, pretty cool. It actually took us a great amount of pain to go through this. So we had to write this weird function, which is called generate grid, which was not the easiest Python programming exercise ever. I do realize and I do understand. I think it was a necessary evil because it actually helped us to see things. I like to see things, and I guess you guys would agree that it's nice to see things. We have also, basically the topic of yesterday's call was basically looking at the ensembles. And not just, not ensembles in principle, but the specific versions of ensembles. So averaging and majority vote. So this is what we have looked at yesterday. And today idea is to look at the weighted ensembles, right? So we have just had this part in the lecture. Let me share the lecture slides just to go over this one more time, just to quickly browse through it. Just to remind you, what am I saying is that you can basically, you can have models, you can do the cross-validation for each model, and you can figure out what's the average kind of goodness score of each model based on the cross-validation algorithm. And then you basically could get this models performing. So I'm just quickly looping through what we saw yesterday. Basically can compute weights from these model performances, and you can treat these weights as an indicator how much you should trust every other model in your series. So for example, you have 3 models, then which model you should trust more, which one you should trust less, and so on and so forth. We saw how these weights or coefficients, they basically end up being something like seats in the parliament, which in this parliament is making decisions about the data. In terms of classification, then it basically votes for the final class. And then each model would be allocated as many seats as the weight of the model. And then you would put this together, you would merge these votes together, and you would just see which data class got the most number of votes from each model. And that would be the one that you would, that would win the election by the parliament. Right, so this would be the bill that would pass the vote. Yeah, and that was regarding the classification. Regarding regression, it was very similar. You do basically cross-validation on that kind of stuff. You get some kind of scores, and then each prediction you multiply with the scores to get this kind of weighted average. So not just average, but weighted average. So you multiply the prediction of the model by its model score, and you sum them up, and that's how you get the weighted average. All right. Does this make sense? Do you want to, just recap and maybe ask a question about this? It's a very simple, this is the simplest way you can get the ensemble. So basically there's no way you can do it simpler. And that's why I wanted to talk about coding. So how do you actually implement this, right? So what are the ways to implement weighted ensembles? Since you guys don't have questions, if you don't have questions, I wanted to go back to the MNIST and Python code. So this is where I get, by the way, one thing. If you have just opened the Ensemble Learning Jupyter notebook, you should run the entire first cell. So you can click here and press Shift Enter, and you will get all these libraries, because otherwise we wouldn't be able to go on with the code, because we need these things, okay? So you need to run that. If you haven't done it, please do it. So run the first cell. This should be important. And then you can go back to the weighted ensemble. I think actually you can do something like this. There is a outline or something, how do you call this? And then you can click on weighted ensemble. And then you can close this. Okay, so what happens here? What happens here is that we load a MNIST dataset. This is how we do it. This is the MNIST dataset. It lives in the library called TensorFlow. So the TensorFlow does not just have neural networks, it also has a lot of different data tutorials. So data tutorials basically mean data sets that everybody uses to do machine learning. So MNIST is one of the most popular data sets in machine learning to test your approaches. If you see new architectures or new models published, they usually have a benchmark in MNIST saying that we have dwarfed all the other performances, and this model performs better than all the rest. And then you have a graph with all the other models and their model on top of it. And you usually use MNIST as one of these kind of benchmark data sets. So this benchmark data set lives in TensorFlow. This is the line that reads in this MNIST into object called MNIST. Unfortunately, this object is fairly complicated. So in order to get to actual,
Excuse me, this screen is frozen only for me or for everybody? I mean, you say TensorFlow, but I still see the visualization of training resample. Guys, for you, it is not frozen. Oleg,
wait.
Do you see the screen?
Yes.
The TensorFlow.
Wait.
Because then.
You mean Dmitri's screen or what?
Yeah, Dima's screen was frozen on the old. Yes, here. Now it is not frozen.
Sorry, this is not the one that you saw. Actually, is my cheat sheet. Is the one that has all the answers to all the homework. So you're not supposed to see that one. So I'm really sorry.
Please send it to me. Please send it to me. I need this one.
Okay, got it. Just in a couple of weeks, in a month's time. So definitely.
We have video. It's recorded.
it's recorded, but you couldn't see much. So I'll put it on the stuff that we have. Anyway, so let's get back. Do you guys see weighted ensemble classification in brackets here? Okay, this is good. This is good. So what I was just saying is that this MNIST object, this one here, it's a complicated object. So if you look inside, it's pretty nasty piece of code and object and functions and methods and whatever stuff. So we need to do some magic in order to release the actual images, right? So the MNIST data set contains digital digits, right? That we saw them in the first homework. So these are the digits that are stored in MNIST. And in order to release them, we need this kind of lot of different stuff. So I'm not actually 100% convinced what is the VStack. I think it somehow takes off the part of the tensor and it transforms it into something. So basically what we do here, we release images and labels from this complicated object, which has like tons of stuff. And then we are saying, okay, the images object, now that the one that was released has this shape and labels have this shape. And then we take only 2000 images and 2000 labels. And we say that these are the train images and train labels, and the 3000 would be the test images and test labels, okay? We also transform train images into data frame, just because it's easier for us to deal with the machine learning. It would be simpler to work with these things. I actually don't remember right now why did I transform it into data frames, but I guess I had some very good reason to do this. So what I do, I just run this cell. Normally I would get tons of warning messages, but thanks to this line here that suppresses warning messages, I only get reasonable output saying that I have downloaded this, I have downloaded that, and I have downloaded this. So original MNIST data set had 55,000 rows. So it means that there are 55,000 images. We took only 2. Right, so for training, used only 2. The third one was for the test. I'm pretty sure you guys saw this one yesterday. So this is the cell where we import decision tree classifier, k nearest neighbor, logistic regression, voting classifier, and then we Igor, what is so how can you interpret this line? What this line does? This model 1 equals decision tree classifier. What exactly it does? How could you interpret this?
Well, we are assigning to the model 1 this decision tree, like classification of whatever.
Is it a ready model? Is it a trained model that will be stored here, or is it just like empty
like
vessel?
A structure. It's like a structure. It's like a vessel. Yes, you need to that needs to be trained.
Yeah. So we basically say we initialize templates, right? Model templates.
Yeah, template or structure, like that.
Yeah. Yeah. Good. Lena, do you remember what this voting equals hard means? From yesterday, what does voting equals hard? Can it be solved? And what would change if it would be solved?
I'm not sure that I get you at all, so I still see weighted ensemble, and I don't know where is.
Gosh, people, seriously? And I was asking you.
And Igor answered to you, you see?
Like, how come? How come? It's like playing games with me. It doesn't even show me that it has this stuff. Okay, well, now...
Igor will frighten us.
Okay.
It was deep fake.
Okay, wait. Okay, so here we go. What do you see now? Tell me, what do you see?
Voting classifier.
Well,
You know
actually,
what? I'll just switch off this.
From my point of view, it doesn't change actually. I see code, I saw code, and I see code, and I will see code during the first half of the day. So actually, what? It's
good.
Okay.
Lena, so we are back here. It's because I had 2 windows of code, and I couldn't. It somehow Zoom doesn't really show you nicely which one do you show, and I was completely sure that I'm showing you the right one. So so we just initialize templates of models here. So we run this line here, this cell with MNIST, right? And then in here, I'm asking, what is this voting equals heart? What does this voting equals heart mean?
For majority voted, I don't know.
Yeah, so what is it? I mean, what it would change if I would change it to soft? And what do you mean by for majority vote? Yes, it's for majority vote, but in what sense do you mean that?
Maybe it's to have draw, not to have draw. So
no, it's not about having not having draw. Having and not having draw is about number of estimators. This is something else. Simon, what is it?
I forgot.
You forgot. Igor, what do you think? What is this for?
Actually, I have no idea why it's hard. So we see 3 models, and we need to vote hard and soft. Actually,
yes,
I was
there is a soft vote and hard vote.
Oh, wow, but actually I was thinking about these draws. Yeah, what Oleg mentioned.
Yeah,
but
I think.
No, I have no idea.
Okay. So hard voting versus soft voting. Hard voting is when your classifiers predict classes like 0 and 1, and then you have to deal with that one. So it could be a draw, it could be whatever other things, but basically it's 0 or 1, and then you're just saying how many voted 1, okay, this many, and how many voted 0, okay, this many. So more people voted 1, so this is 1. When soft voting is in place, then you collect probabilities. You collect probabilities. So basically each classifier is saying, I think this is 1 with this probability. And then you're saying, okay, what is the average probability of 1? Okay, this is 55%. What if, Lena, if my average probability of 1 is 55%, would I go for 1 or would I go for 0?
Do you go for 1?
Yeah, I would go for 1 because the probability is more than 50, right? Which means that the 0 has 45% probability. If this would be a 3-class classification, Oleg, if I would have 3-class classification and my average probability of class 1 would be 55%, would I still go for class 1 or would I need to calculate probabilities for class 2 and 3? I can't hear you, you are muted.
sorry, I think that you need then to calculate 2 and 3.
Do you? So what would be the probability, what would be the maximum probability of the other 2 classes? What would be would they be able to overrule the probability of the first class?
It's probability of what? Once again, it's probability of the model itself. Because every model...
You get 3 models. Each model is voting for probability for the first, second, and third class. All right? Then you say, I'll take the average of all 3 models for the first class, right? So what is the average of the 3 classes, 3 models voting for the first class? So it would be 55%. So 3 models on average are saying that this image belongs to the first class with a 55%. But you also have class 2 and class 3. Would you need to calculate class 2 and class 3 in this case?
In case of hard?
In case of soft, when you predict probabilities.
In case of soft.
Simon, what do you think?
I think we do not need to calculate the another probability because 55% is much more than 33% of random probability.
Okay, but can it still be second class?
Second class, yes, but second and third class, you know.
Yeah, second or third class.
Yeah, so the probability of second class could be a maximum 45%.
Yeah, so basically there is no way that the other class would overrule the probability for the first class, right?
Of course, it depends on the threshold we put, because sometimes 50% threshold could be moved up or down.
Yeah, but in the tree class classification, it's not about threshold, it's about the majority, the highest probability, right? So, but we haven't really discussed the soft voting yesterday. So I think I completely understand. So you guys, it's fine that we haven't discussed that. It's just for me to kind of wake you up a little bit. So just run this cell, just run it and get these templates. What is happening here? Igor, what is happening in this cell here? What am I doing here? What are these weird lines here? What is this code?
Using randomization, you're trying to fit to teach your model. So,
what do you mean by using randomization? Can you explain that bit?
Well, you use this NP function random, and you seed and you set seeds like equal 11, 11. That means that the system will get some kind of like template of a random like items, yeah, and then it will pass us this to the model 1, and then
model 2, model 3, and so on, right?
Yeah, yeah, and model 6. Yeah, okay. And actually model, yeah.
So in a very simple terms, what is this random seed thingy allows me to? What is it that it allows me? What is it that it helps me to do?
This helps you to make this random patterns to be like frozen, and this will allow you to recap your randomization pattern in the future. So this means that you will get equal results of randomization in any point of time.
Yeah. So basically, if I rerun this in a month's time, I'll get the same results. And if you guys run it together with me right now, and I hope that this is what you will do right now, you will get the same models as I do. So I should have the same models as you would have right now.
Excuse me, about this randomization, I understand how it works, but where it is in separate line, and we do not mention this the link to this random seed in the model fit.
Yeah.
So how model fit takes something into account?
So how does so let me interpret the question. The question is, since this line here, it's not linked to the model fit line. So there is no variable that is shared between these lines. How does this line, or this line for that sake, knows that we have fixed the random seed? I think the answer is like this. There is a random generator, pseudo-random generator, that is always there on the background. What this does is it's just saying that initialize your random generator at this particular state. And once you initialize the random generator, every other function or every other code that asks for a random number, so imagine that there is a world of wonder and there is a random generator that lives in somewhere backyard of the forest. And then the Red Hat comes to this random generator and saying, Mom, ask for a random number. Can you give me a random number? And the random generator is giving the random number. But now we came before the Red Hat and we said, hey, random generator, can you turn yourself into this initial position? And it did. And then when the Red Hat comes, it will give the Red Hat the same random number. So once we fix we put this random generator back together, once somebody would ask for a random number, it would give the same random number. It would start giving the same random numbers. So whoever or whatever happens after the random seed will produce the same random numbers. And once we fix it again, the same random numbers start to get through. The same random numbers start to get through. So they shouldn't be connected because this is acting with an external actor, which is the same shared for all the actors inside the system. So all the actors inside the system, they talk to the same random generator. And we are like fixing this random generator for everybody.
But in this case, should we repeat this line before every model fitting?
So why do I repeat this line for every model is because I just want to make sure that they all start with the same random numbers. I don't exactly remember why did I end up having things like that. I might have had some reasons for this, but I can't really recall it right now. Normally, I think it would be actually okay if you just have one random seed fixed, just one in the beginning. It should be enough because you don't really care what kind of random numbers go inside each model because that just doesn't make much difference. But I don't know. I don't remember the reasons for me for fixing these 4. That's the true and honest answer.
But model fit, why it needs a random generator? We have two. We have one set of trained.
Okay, so the question here is why do we need? Why does a fit function needs a random numbers, right? So what are the models that we have here, Simon? What are the models? Do you remember what are the models?
Yeah. We have here the decision tree, neighbors, and logistic regression.
Logistic regression and k-nearest neighbors, right?
Yeah.
So what do you think? Let's take k-nearest neighbor with a number, with any number of k.
Okay.
Lena, can you give us a number of k?
5.
5. And Lena picked up a golden K that is used all over the place. How cool is that, huh? It's just like out of blue. Cool, 5. So 5 it is. Simeon, now the question back to you. The ball is on your side. Think about this. K nearest neighbor, which is, remember what, right? So it calculates distances to all points, and then it picks up 5 closest, and then it basically assumes the class of the digit based on these classes of the nearest neighbors, right? So now, thanks to Elena, we're looking at 5 nearest neighbors, okay? So the question to you all guys, how come you may need random number in that process?
First, I need to point 5 random centers of just 5. 5.
Okay, what is 5? Random.
Yeah, just in this case, I would choose random to find the random starting point for the calculation of the distances.
Wait, but you have specific starting points to calculate the distances because you have trained images, so you do not really start randomly in here. You actually, for each image, you calculate distances. There's no way around it. But where possibly you may need random generator in this process. So this is not the random, this part is not random. Calculating distances has to be done all for all. So you need to calculate distances from all images to all images. There is no way around it. There is no randomness involved.
Only in case of I'd like to calculate the clusters, for example.
Okay, what do you mean by that?
I mean, then I can randomly choose the 5 centers of the clusters and to start the calculation of this.
But this algorithm is not. It's not used for clustering. Yeah, it's not
it is another algorithm. Algorithm. I agree.
So my question is still holds. Where in k-nearest neighbor you may need to use randomness? Lena, can you help us? Where possibly randomness can creep out into this algorithm?
Just to sort the training test. But
just to sort the training test. You don't really sort training, neither test.
So I have no idea.
Oleg, Igor, Lena, help out.
So when do we use random?
Yes, when do we use randomness, stochasticity, chaos, the theory of chaos in k-nearest neighbor? No, I'm just kidding. There is no theory of chaos in the k-nearest neighbor. But where do you use stochasticity? Where things may get undetermined in k-nearest neighbor.
If the same number equal will be, yeah?
Can you elaborate on this? What do you mean by that? It's getting close. I can feel the heat.
If it will be 50% is a class 1 or class 2, and then we need to set.
Okay, but we just been given a perfect number by Elena. She's just said, you know, guys, don't worry about this. We have 5 classes. So it means that there is no way you can get 50-50. But this is a binary case. If you have multi-class case, you're absolutely right. You can have one of each class. You can have 1, 2, 3, and 5. And then how do you decide, right? So this is where randomness can come along. You need to decide. There is yet another way how randomness can creep into the k-nearest neighbor. It's when you, for example, you have your calculated distances, and it turned out that 10 images lie on the same distance to your point. And then which ones do you choose, right?
Yeah.
Not clear. So maybe you toss a coin, you roll a die. It's all up to you. And this is where randomness can creep into the k-nearest neighbor algorithm.
So we use we use random for situation like 50-50.
Yeah, like or like a tie in more expanded understanding of this.
Okay,
it's
clear.
It's not just a prediction, but it could be selecting nearest neighbors where you need.
Yeah. For example, we have 10. For example, we have 10 neighbors with the same coordinates. The question, which 5 we shall take out of 10?
Yeah, yeah, for example. Lena, does it make sense?
Mm-hmm.
Okay, good. So this is where we need randomness. That's why we fixed randomness, just in case, to make sure that everybody gets the same stuff. Here we, by the way, I'm really sorry. So you can actually, looking at my code, you can see that I'm not a perfect, I'm not a really good programmer. I would normally call this model not a model. So when I assign voting classifier to model, it's basically not a good way to do it. In the very least, I would need to call it something like a voting model or something like this, so that you know that this is a voting classifier. This is an ensemble. So forgive me that that's in. Now that I train these models, now I predict these models. I use test images to predict, to make predictions using all 4 trained models. I just use model 1, predict, model 2, predict, model 3, predict, and so on. So, and yeah, do it, please. I mean, unless you have questions about these lines, do they make sense? Lena, does this make sense? Igor? So you just take a model, you train it, you have done the hard work. Now you can rip off the good things in life and finally use it to predict your test images. Okay, make sense? Okay. And now we can evaluate. We can say, all right, so we trained them, we tested them. Now we can compare the tested performances. Oh, by the way, here I actually predict things, but I'm not using them right here. I'm using a function score. I'm saying model 1 score test images, test labels multiplied by 100. And this is the accuracy that I get. So if I look at this, I'll get this accuracies. Okay, the torture circle, the circle of torture is continuing. So Igor, how can you interpret these values? What can you say about this stuff? What is it interesting when you look at these accuracies? What is it that jumps right ahead of you and like, oh, but this is interesting. This is something I should point out. Igor? Lena, since you have your mic on, maybe you could, you know, jump on it.
Oh, why Igor? Why Igor? Why?
Why always Igor?
Yeah.
You know what? This is a problem. We have like 1, 2, 3, 4 choices. I can always ask myself, or I can ask Alexander. But this is a fairly low entropy people. They will not produce anything interesting. So I would prefer to ask Igor because it has a lot higher entropy. It's interesting.
So you have some specific seat for for Igor.
And
Yeah,
it's been fixed a long time ago. Can't refix it anymore.
yeah, and actually having fun with that. Yeah.
Good. The best thing is that you should have
please. Dominate, please. Use. But I'm sorry, I had a problem with my sound. So can you please repeat the question?
Let me give you context a bit. So we trained 4 models here. One is a decision tree model, nearest neighbor model, a logistic regression model, and the ensemble. Ensemble of all these 3. Okay, so we just put them into ensemble. And here are the accuracies of these models on the MNIST data set. So my question was, can you jump ahead and say, hey, this is interesting. This thing about this output is looking weird or somewhat extra. So what is it that maybe sounds interesting?
Yeah, it's interesting because actually it's expected to have higher accuracy rates of ensemble model of the model which consists of sums up all 3 algorithms. But in this case, we see that decision tree is better than ensemble model. That's really interesting.
No, the decision tree is not better than ensemble model, but nearest neighbor is better than ensemble model.
Oh, sorry. Yeah. Sorry, I had a look into different line. Yeah.
Yeah.
Nearest neighbor has higher.
I absolutely agree with Igor in the sense that looking at the ensemble, you're like, okay, ensemble, what's wrong with you? You have 87% and the accuracy of the nearest neighbor is 88. Something went wrong here. Simon, what else can you kind of point out? What is it that may be interesting? Looking at these accuracies, is there anything else that kind of looks at you and you're looking into Abyss and it looks back at you. So you look at this output and it looks back at you. What is it that looks back at you?
No, in fact, I'm confused only by decision tree. That there is a huge gap between the other models and the decision tree.
Okay.
For the rest, it's okay. I mean, for me, for me, it looks normal that ensemble is a bit lower than the best models.
So why does it for you it makes sense? Why does it make sense for you? What is it? Why is it reasonable?
To some extent, the ensemble is impacted by every model in the ensemble. So it's to some extent it is average or weighted accuracy of all the models inside. So that is why if there is bad model inside the ensemble.
Exactly. Sorry.
For this, let's say for this test data, it could be less, but maybe it will play back, in different test data set, So could be, absolutely possible. So what Simon was saying is that if there is a bad sheep, it may drag the ensemble together with it, right? So maybe we should trust bad sheep less than we trust the other models, right? So maybe we should be trusting the other models more than this one model that we see here. And that is the point of the weighted ensemble. So we need to somehow let the weighting ensemble, this ensemble model know that it needs to trust nearest neighbor and logistic regression a bit more than it trusts the decision tree. So how can we figure out how much it should trust one, not the other? So if we get back here, I'm just writing here that 87 is not perfect, is not something that I would be impressed by. And here I'm just saying that there is a parameter weights in the voting classifier that you can specify the level of trust of the ensemble into each of the models. And here I just propose to replicate the basic ensemble using this parameter weights. So just to make sure that everybody sees this, here is the voting equals hard, where I tortured Yelena. I was asking her, why is that thing here? And then comma and weights.
So this is an array of weights, and basically each weight is saying how much you should trust this model or you should trust the other model, okay? So I have a question for $100. How do I replicate a basic ensemble with these three numbers? So I have three numbers here. I have to write three numbers. What are these three numbers that will, let me just write it X, X, and X, or maybe X1, X2, X3, so that you guys know that these are different numbers, or they could be different numbers. So what are these three numbers that will allow me to replicate the basic ensemble? Lena, what are these three numbers? What would you recommend? What would you suggest? Basic ensemble, like just majority vote. What would be the trust numbers? How much you would trust each model to replicate a majority vote ensemble?
So I need randomly choose now something.
I don't know. I don't know. Maybe. Go ahead. Try. Tell me these.
Like, you mean that we need to I don't know.
So what I mean is that we get 87.6 here, right? What I mean is that can you choose these three values so that this model here will act exactly like this model here? I give you a couple of minutes, guys. Do it yourself. Try to find numbers that will replicate the performance, would be exactly the same, would make this model exactly the same as the model which did not have any weights here. So what are these weights that will replicate the basic majority vote ensemble? Just give it a couple of minutes. Just think about this. Try out a couple of values, see if it works, and then let's discuss it again. Simon worked? Good. Alec, did it work?
Approximately, yeah.
That should be exactly like this.
Yeah, I found the answer, and I'm, frankly speaking, surprised.
Surprised?
I mean, I applied weighting approach, and I surprised by the result.
Okay.
But
okay. Lena?
I have stupid question. So it must be 0.33, like average, yes?
Yeah. Why not?
But
What if we try? What if we try just 0.33, 0.33? What if we try to 0.33? Do you mean this?
yes.
Okay. Da, 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 da. You were right. How surprising is that? You just take all the models and you treat them equally, like egalitarian world. You can even without this, you don't need them to be sum to 1. You can just say 1, 1, 1. I don't care. And that would be the same stuff. See? Stupid question. Where is the stupid? You were promising me a stupid question. I want stupid questions, please.
Yes, like if you add accuracy, 3 accuracy and divided by 3, it will be 80 something, not 87.
Perhaps, I guess. I'm not sure. The thing is this not working? Yeah, go ahead, Oleg.
It's necessary, I think, to normalize, yeah. So to number of true predicted values. if you recalculated correctly.
So wait, just to not to confuse everybody. So what Olena is saying is that how come you guys get 87.6, provided that if you would take average of these three, you would not get 87.6. Simon, how come? By the way, what's the average? I don't know. What's the average? Does anybody know what's the average?
Yeah, the average is about 80.9.
80.9. Okay. Does it? Okay. I don't trust you guys. No, I trust you guys, but I just want to see. All right, 80.9, right? Okay. So how come? Simon, how come? This is important. This is a bridge. This is a big failure. What's happening? What is happening here? Oleg, what is happening?
We calculated this effect yesterday.
We calculated, we have seen the same stuff yesterday, right?
Yeah. It shall be normalized, yeah, so.
Normalized, so we normalized it. It's divided by 3. Fairly nice normalization to me.
No, I mean that you need to calculate number of past values and then to divide it by of total number. But actually it's the same, yeah.
Igor, what do you think? Why do we see this discrepancy here? What's the problem?
No idea. No idea. It
this
seems
is like strange,
it seems
right?
it seems like we get this high number of ensemble because if for any reason we have I think the first thought is that due to this hard voting we have higher rates of NN and LR, and actually if those two models had right answer, so in ensemble we really will get right answer. But if you just sum up and divide by 3, we are losing this idea of hard voting. So in this case, actually we get how to say среднее значение.
We get different values.
We get simple average, but in case of ensemble model, due to this hard vote, we should get higher rate.
Yeah, so basically, I think I agree with Igor in the sense that what we see here is that the errors of the decision tree and 2 other models, they are not correlated. So meaning that when decision tree make an error, the other 2 are good. And since there are 2 of them, and this is a majority vote, then 2 is a majority in that sense. And they overweight the incorrect prediction by the decision tree. And that's why they pull the accuracy more towards this 87.6. And you can see it, if I take the average of these 2 guys, this is exactly what we get, right? So it turns out that these 2 guys, they make similar mistakes. So when they are wrong, they are both wrong. And it doesn't really matter what the decision tree is now voting for. If these both are wrong, then the entire thing is wrong. But then when these 2 models are right, and it doesn't really matter what the decision tree thinks, and they pull since they are right in quite many cases, they pull the overall accuracy of the ensemble towards this 87.6. So it's not exactly working. So it would work as average, as what Elena proposed. It would work as average in the case they would all make the same mistakes. They would be doing mistakes at the same time. For example, in decision tree NNN and LR, they would be wrong in this I don't know, 12% of the time, and they would be correct in all the other cases, then we would get the average of the performances. They would be correlated, errors would be correlated. But since they are not correlated, decision tree is somehow, how do I call it? It's conceptually different. It's conceptually different. It makes mistakes on a conceptually different level. That's why we don't see the average. We see more tilt towards these more accurate models. Does this make sense, Lena? So they are conceptually different, and that's why you don't see the average. This is somewhat, that's what ensembles are used for. If you don't have models that are conceptually different, then you get the worse performance. Okay, okay, we got it. So you can use weights to reproduce basic ensemble, but can you use weights to reproduce, well, to get something better than 87.6? Oleg, what would be the approach, the basic, the simple approach? How could you, say that trust this model more than the other model?
To increase weighting factor for model which I trust more.
So which one, for example, you would recommend to increase, and how much?
We can make 0.2, 0.4, 0.4, for example.
0.2, 0.4, 0.4. Okay, let's give it a try. So, Lena, which models Oleg decided to trust more based on this weighting?
With second and third, so logistic regression and KNN.
Yeah, and somehow discriminated against decision trees, which should be more living in a more open society, I think. So Oleg discriminated against decision trees, and you know what? It got so much better. It got 88.2%. But there is a question, there is still a question, what if there is a better combination? What if there is a better weight kind of schema that can get us better than 88.2? How come? How do we know? How do we know, Semyon?
We can use weights. Instead of weights, we can put the accuracy of every model.
Mm-hmm.
And then we will receive the weighted.
We can use accuracy of the models, but wouldn't I somehow compromise my test set with this? Wouldn't I produce an ensemble that would be more optimistic about my test set than it usually would be?
Of course, we play with test now. Yes, I agree with you. But anyway, if you put that accuracy, we receive 89.
Yeah, so what would be a way around this, guys? What would be the way around this?
To get optimal with cross-validation.
Exactly, let's do cross-validation. So here we do cross-validation. In fact, so don't be afraid of this long cell. I mean, do be afraid of this long cell because we're going to work with this. But this is a copy-paste from the homework number 1, right? So this is what you had to do in the homework number 1. I know that many of you had a trouble with this. I'm going to look through it and we're going to do it together right now. So we could fix it, see how it works, and try to find the optimal parameters for the models. So what we're doing, we're taking the training data. We are producing four folds, meaning that we divide our data into 4 equal chunks. Then we take 3 chunks as the training data and the 4th chunk as a validation set. And then we take another one as a validation set and 3 others as a training data, and so on until every chunk gets a chance to become a validation set, right? All right, everybody? Does it make sense? Do you remember what's the cross-validation algorithm? Any questions? Because it's important to keep in mind what is it that we want. So here I just create a list of models. So we have model number 1, model number 2, and model number 3. This is a copy paste again from your homework. Sorry, this is wrong. That's why I have this RMSEs and weird comments and that kind of stuff. So we will basically be coding this throughout. We will be doing this together with you. So first of all, we will be collecting validation fault accuracies for each of the models. So we would need to have an average cross-validation accuracy for model number 1, average validation accuracy for model number 2, and average cross-validation accuracy for model number 3. Lena, a question, a major one. What is the, how many, what's the size of this vector? So this is a vector that should store an average cross-validation accuracy for each model. What's the size? For each model, that's the keyword. For each model, how many models do we have? Huh?
We have 3 models.
We have 3 models. So how many values do we need to keep in this thing? We need only averages across all folds of the cross-validation algorithm for each model. So each model would have 1 value.
Okay.
So how many values do we keep in this?
3 for each
so
model.
We need to keep just three values. What is the good NumPy function that initializes a NumPy array? Which ones do you know? Which ones maybe you kind of heard about? There are 2.
np.array.
np.array, which is true. So we could write something like this, array, and then something like 0, 0, 0, just for starters, right? To initialize stuff. Do you agree with me, guys?
Mm-hmm.
Is there any better way? Simeon, Igor.
We can write NP array, and inside it we can put the number of models. I mean, we can to some extent automate the calculation of initial zeros in the array.
Okay.
But for the rest, NP array looks good.
Okay. There is a function called NP zeros. Have you heard about this one?
Mm-hmm.
Yes. NP1
so what it does?
As well. Yeah.
Never. I have never heard about it.
You have heard about it yesterday. I talked about it yesterday. No way around it. So what it does, Igor, what it does, since you have never heard about it, you should not know what it does.
I can just assume that it puts zeros to the NP array.
Gotcha. What is the parameter, the input parameter of this function? Lena, what is that it goes inside here?
Models.
Models. And what it does with models?
I don't know. So
how do you check this? Okay, so I gave you a function and you have no idea what the function is doing. How do you check what is going on with this function? What's the function is all about?
Print it.
One way is to print it, but the other one is just to type brackets and see what this drop-down menu says. It says that it returns a new array of given shape and type filled with zeros. How cool is that?
Cool.
And it says that the first parameter is shape, and it even has some kind of example. It says the shape of the new array example is 2 and 3 in the brackets, or 2. So what if we want to create an array of size as many models as we have, filled with zeros? So what should I write inside the brackets? Simon, what should I write inside brackets?
Let's try len and then brackets write models.
Len models. Hey, that's so cool. Are you saying this is so short and so beautiful? Can't be happening. It's so nice. So what we could do, we could just take this off this cell and test it. Well, we could also initialize models as well, just to make sure that it works, right? So, hooray! And the cool thing is that if I add more models, it will automatically increase the size, right? That's the programming, the power of programming. You don't need to, go ahead and just type again another 0 and comma and all sorts of things. It will do it for you, which is pretty nice. Okay, now there is a something inside. So let me do it like this. Since I have a great zoom, so it does something inside the loop. But what is it looping over? Oleg, what is it looping over?
Sorry, it's looping over max depth. What is this max depth?
No idea. No idea at all. What is it supposed to loop over? This is looping over some weird stuff from last time, from the homework.
Yeah. We want to loop through the for weighting factors. Yeah, so to
weighting factors. No, not exactly. Where we are? What are we trying to do? What are we trying to do?
We want to run through every fault. Yeah. But we want to find optimum, for weighting coefficients, right?
No, Simon, what is the plan? What is the grand plan? Why are we even starting this stuff?
So we try to calculate the weighted, the average accuracy for every model.
Yes. So we are trying to calculate accuracies, okay? Accuracies, average accuracy across faults for every model. We're not working with weights, Oleg, here. We are not working with weights. What would be the weights? Lena, what would be the weights at the final step when we are done? So just remember that we want to get these 3 values here. Values. How do we get these? What are these? What do I put inside each one of these places when we are done? When everything is fine and rabbits are flying around and everybody is like happy and there is nobody dying and there is no cancer, what is going to happen here? What am I supposed to enter into this and this place?
Accuracy of every model.
Accuracy of every model, right? The average accuracy over 4 faults, the cross-validation value, right? Lena, do you copy? This is very important because if you guys don't understand what are we trying to do, there is no goddamn way we can do it. If you don't see a goal where we're going, it doesn't make any sense. So what we will output in here is what's the average cross-validation accuracy for decision tree over 4 faults, right? So we will get the accuracy of the first fault, the second fault, third fault, fourth fault. We will average them up and we will put them nicely into this array.
So then I didn't get the task from the beginning. I thought that our task to find optimum for these coefficients, that we.
Well, we kind of assumed that this would be optimum. This would be better.
Okay.
So the premise is people normally, automatically, instead of doing this, like what I was doing, they never had Oleg to ask. So Oleg told us use 0.2, 0.4, 0.4, and you will be fine. We tried and it did indeed work. But normally people do not have access to Oleg. They cannot really call him and say, hey, Oleg, what are the ways that I can use in my machine learning problem here? So what they do instead, they run cross-validation algorithms and they get accuracies for every model across for as many faults as they have. And they use these accuracies as the weights, as a trust coefficients, right? That's what they do. They look exactly what Lena did. She looked at the 67.6 and she was like, you shouldn't trust this model too much, right, Lena? And then you looked at the, for example, nearest neighbor and she was like 88.4. This is pretty trustworthy, right? So we will use these values as a trust coefficients for the weighted ensemble. Do you guys copy this? Do you, Roger? Roger. Hey, can't hear you. I can't hear you. There's some problem. There is some silence.
So this, how it's called, class voting, yeah? So it actually recalculates weighting factors, yeah? So it shall not be in sum up to be 1, yeah. So
yeah, it doesn't have to sum up to 1. It doesn't have to be any kind of range. It's fine if it's like a 67.6 or is it 0.67.6, whatever you have. It just needs to be some values, and they should be comparable. If they are comparable, they come from the same range. Perfectly fine. Doesn't really doesn't mean it's not important. They should be comparable, meaning that you can't really sample from millions for one model and sample from onces from the other model. You should be really sampling from the same ranges, but otherwise it's fine. So you can use accuracies as weights for your model, for your weighted ensemble. Lena, does it make sense? Tell me.
Does it exist another way, not about using accuracy as a weight?
Oh, yeah, you can use anything you like. You can use F1 score. You can use all sorts of performance metrics. It's not just about accuracy. Any value that says that trust this model more than the other model, perfectly fine.
But may I ask a stupid question?
Great. Well, actually, I love stupid questions. Please go ahead and shoot at me stupid questions. Don't look at Alexander. He's just an observer here. I will switch him off if you like, and just don't be afraid. Just speak up.
Oh, I look to Oleg, and actually I'm frightened by Oleg because.
Oh, you're frightened by Oleg.
He is really cool in this. Well, actually, and Semen as well. Yeah. Actually, my question is, okay, we need to find like weight, yeah. Yeah. And I can assume that weight for DT should be as low as possible, maybe, and weight for NN should be highest among all these three. And LR should be like somehow less than weight for NN. Yeah. So okay, then my logic is I'm trying to divide my data set into 4 equal folds. Mm-hmm. That's okay. But then I will put all the data through 3 models, like 12 times. So I'm about to put like 4 folds for DT, then 4 folds for NN, and 4 folds for LR. And then
aggressively agree.
Okay. Then you should do kind of single weight. Yeah. So you will get 12 weights, 4 per each model. Then you will start to the same problem. In which way you should like average, or maybe like, I don't know how to lower the weight of DT and how to like make it higher for NN. So as far as I can get, dividing all the data set by 4 folders, won't help us much as far as I understand.
So this is a very advanced question. I don't know why you call it stupid. It's fairly advanced. What I would say is that you just take the average of these folds and for each model, and you get one value for each model. And ideally, we don't know, we cannot guess, but ideally these values that you get, the average fold values. So you were saying 12 values, right? Because you were saying 4 for each model. So now if you take averages of each of these 4 groups, you will get 1 for each model. So ideally, these values should be close to what you see in here, okay?
Yeah.
Ideally. We cannot, unfortunately, use this information that I'm now looking at here, because this is a test set. We are not supposed to know the test set performance until we try everything on the train data. So this, the fold thingy that you were describing, it's meant to find out what are the good coefficients without looking at the test set. Okay?
Maybe yes, but what about cross validation? Why is it cross? Because actually cross, it means that the same data set should be put into different models, and in this way you will get like an accuracy of each model. So I can't really get. Maybe we will see this in numbers, but I can't from the logic perspective. I can't see how these 4 folds will help us to get the ideal.
Yeah, I got it. So the thing is, you have only ladies and gentlemen, this is a very good question. You have training data and you have test data. So what am I trying to do right now is I try to compute the ensemble weights based solely on the training data. Now my question to you back is, what happens if I just train a model on the entire training data and I verify it on the training data? What happens to the score? So I take decision tree, I take my training data, I train my decision tree on the training data, and then I compute the score on the training data. What happens to the score?
Well, if training, the score will be higher because
it will be almost 100%, right?
Yeah. It's overfitting of the model because it's like you test on the training data. No.
Exactly, right? It doesn't make sense because your models will be overfitting the data, and you will not see this picture. You will not see these scores. You will not see an adequate performance estimates. You won't see adequate performance estimates. So do you see where am I kind of getting? Where am I getting with this? Okay, let me give you another one. So what happens in the cross-validation algorithm world is that you take the training data, you split it into, let's say, 3/4. So it's 75%. You train your decision tree on 75%, and then you verify it on this last 25%. Can you now guess what is it why we are using this cross-validation algorithm here? So instead of training the model on the entire training data, we train it on the 3/4, and then verify it not on the same data that we have trained it on, but on the left out piece.
So by training with let's say 3/4, we may get like a better. We think that will be better trained model. Then in case of decision tree, we will test it on a 1/4 data set, and because of the lack of accuracy of the algorithm, we should get less accurate performance than without the division of the data by 4-fold. Yeah,
exactly.
So this is the main point of what we are about to get.
Yes.
Mm-hmm.
we are getting something close to reality, something close to what will actually happen when we give a model unseen data, completely unseen data, something that model has never seen. This course, this averages across 4 folds will be more like reality, right? That's why we do cross-validation algorithm in the first place. Lena,
Okay.
does it make sense? Oleg, Simon, does it make sense?
Yep.
Lena, I can't see it. It's like, yeah, sure, I got it. This is so cool. I finally got it. I want to see that. Can you elaborate? What is not? Is it there? You're just, you're doing this deep inside. You're like, yeah, running around the room and like, yeah, finally. No?
Mm-mm.
No? Have you seen this Harold meme? Like this guy is like, okay, let's have a break and let's come back here at 10 minutes. I'll give, and you guys all go away and Lena stays and she can finally ask me questions. No, everybody goes away then let's make a break and come back in 10:34.
Okay, thank you.
Thank you. I think it was an amazing question. I hope you satisfied with the answer. That's what I hope.
I hope so too.
Короче, типа, я не сильно поняла, что происходит от слова совсем, поэтому...
Так, а в чем, что конкретно ты не поняла?
Я, в принципе, не поняла вопроса от начала, поэтому...
Не, ну, у меня был, я просто чуть-чуть, я как бы, сори, что влез, но у меня был просто вопрос. Вот мы взяли на тестовых данных и получили аккуратность ДТ 67, да?
Да.
Каким макаром мы получим меньше, чем 67? Так как на самом деле нам надо уменьшить вес вот этой модели явно. Ну, то есть это как бы очевидно. Тогда мы используем вот этот cross-validation. То есть мы берем не все тесты, а мы берем их там 75%. Мы тренируем...
Мы не берем тесты. Смотри, мы не берем тесты вообще, потому что тесты нам недоступны. Тесты — это то, что компания получит там в следующем квартале, грубо говоря. А у нас есть только наши тренинговые данные, то есть только то, что у нас есть на данный момент. Это очень важный момент, потому что мы не можем знать вот эти цифры. Вот ты видишь их 67,6, думаешь, так, надо понизить срочно степень, короче, важности ДТ, а на самом деле ты не знаешь этого. На самом деле все, что у тебя есть, это тренировочные данные.
Ну, вообще да. То есть мы берем вот эти тренировочные данные, мы берем только не все их, да, чтобы выйти сразу на 67, а мы берем их там 75%, а потом пробуем их оттестировать на оставшихся 25%. И исходя из того, что алгоритм ДТ явно здесь не подходит, ну как бы, ну он подходит, но он
не так работает хорошо, как другие.
Да, то мы как бы взяв 3/4 от вот этих, как они называются, данные?
Тренировочных данных, да.
Тренировочных данных, и оттестировав их на тех же тренировочных, но 1/4, мы явно получим результаты как бы хуже, чем мы видим здесь. И тогда мы сможем, типа, как...
Это, кстати, не факт. Это не факт. Мы не знаем, что мы получим, потому что это тестовые данные. Они отличаются от тренировочных данных. То есть мы почему делаем вот эту вообще кросс-валидацию на 4 фолдах? Потому что мы хотим получить такую оценку, более объективную оценку того, как работать модель будет на внешних данных, которых она раньше не видела. То есть она будет как-то работать, и нам надо понимать, как она будет работать. И в соответствии с вот этим вот пониманием мы будем выбирать вот эти веса. Лена, тот вопрос, который я тебя спрашивал, я тебя спрашивал, чего написать вот сюда, вот вместо вот этих циферок. Потому что вот эти циферки — это то, что Олег дал буквально вот, с болты. Сказал какую-то фигню, да. И получилось клево. То есть он просто посмотрел на эти цифры, и он такой, так, типа, надо понизить, значит, важность ДТ. Вот то, что Игорь сейчас говорит.
Окей, я понимаю, что, типа, нам нужно дать больше веса, те, которые более адекватные модели. Но моя идея была о том, почему мы вообще уверены, что, типа, нужно ориентироваться на accuracy, почему нету другой оптимальной штуки, которая бы подобрала нам весы. То есть я об этом.
Хорошо, да, это хороший вопрос, на самом деле вполне справедливый. А на самом деле, ну, ответ такой, что типа, а чё нет? Ну, то есть, типа, ответ такой, что люди так делают. Вот такой вот подход, что берется какая-то метрика, не обязательно accuracy. Это может быть F1, это может быть, если тебе это важно, то это может быть recall или precision или еще какая-то фигня. И просто вот сюда вместо весов запихивается вот эта самая степень работы, степень того, насколько модель работает на вот этих тренировочных данных. И все, это типа, ты просто это используешь как вес. То есть ты смотришь, ага, 67,6. Если бы сюда ты написал 67,6, а в те 88,4, 86,7, был бы приблизительно вот такой же хороший ответ, как мы бы получили, как вот здесь вот мы получили. Вот. Что-то типа того. То есть проблема в том, что лучше, я не знаю способы, как получить веса. Олегу все время звонить в Киев и говорить: слышь, Олежка, посмотри, пожалуйста, тут какие-то непонятная херня, какие мне веса использовать? Тоже как-то неприятно, наверное, человеку будет сложно отвечать постоянно. Поэтому люди придумали вот такой способ. Типа берешь, там, делаешь кросс-валидацию на 4 фолдах, подсчитываешь среднюю точность и запихиваешь туда в качестве весов.
Okay.
Вот.
Это просто самая простая аппроксимация, иначе нужно делать полный перебор по тем же весам, а это очень долго.
Да. Так, давай на перерыв, и потом мы еще поговорим про кросс-валидацию. Игорь, ты что-то хотел спросить?
Не, перерыв, сори, я...
Давай, немножко прервемся и вернемся сейчас к этой обсуждению.